A data logger is attached to a coil so that it registers a positive EMF value when the current is flowing up the front of the coil. So when it flows this way, hello. When it flows this way, somehow I was locked on. When it flows that way, that's positive EMF. Okay, so let's just look at this thing, right? Okay, take your right hand and pretend you're wrapping it around a coil. Okay, notice that when the north pole is on the left side, that's when the current's flowing up the coil, right? So in this case, in this particular instance, as that magnet approaches, we're going to get a positive EMF spike. Okay. Explain why the motion of the magnet induces EMF in the coil. So use Faraday's law, right? The EMF is the rate change of magnetic flux, right? And that as the magnet gets closer, the magnetic field increases, which changes the flux over time, which induces an EMF. All right, let's see. Draw a graph of how the potential changes with time as the magnet passes through at a constant speed from left to right. Okay, let's see, B. I think we can do this. Here's our EMF. Right, so it's passing through. As it approaches, remember, the north pole's approaching, so you want to repel that north pole. So the current's going to flow up the front of the coil, right? And up the front is a positive EMF. So we're going to get a positive EMF spike, right? And then it's as it enters the coil, right? As it recedes from the coil, you'll have a south pole receding. Well, the best way to get a south pole to recede, to keep it from going away from us, right, is to make a north pole on this side. Well, doesn't that make the EMF go down, right? Okay, so we're going to draw sometime later, depending on how long the coil is, an equal downward spike. These guys are equal, okay? So that's our B, right? It moves at a constant speed. These guys are equal. First an upward spike, then a downward spike, okay? All right. C, draw a graph of how the potential changes with time as the magnet passes through at a steadily increasing speed. All right. So C. Okay, so what we're going to have is it's going to enter the thing at a lower speed. So we're going to get a small positive spike. And then sometime later, depending on the length of the coil and the length of the magnet, right, we'll get a bigger downward spike. Small, big. All right, so let's see, steadily increasing. Draw a graph of as it passes steadily decreasing speed. Well, I can't. D. Okay, so steadily decreasing would just be the opposite of this, right? Okay, so it enters the coil at perhaps that, whatever that velocity it's entering here, right? Okay, and then as it exits, it's going slower. So this is a smaller downward spike. Could be wider too, right? These spikes could be wider, right? Okay, so this is big, small. Okay, so E says the coil has 500 windings and a diameter of 3.5 centimeters. In one instance, the magnetic field goes from 0 to 0.315 Teslas to the right in 0.52 seconds. And that's as that north pole magnet approaches, probably, right? Okay. What is the rate change in flux in the coil? Of flux? All right, so E, remember that EMF is minus N d flux dt, right? Okay, so the rate change in flux is just going to be, in this case, flux is, in this case, it's the change in B. Area doesn't change, right? And then presumably the cosine is, the angle's 0 degrees, so cosine, it doesn't factor in, right? Divided by time, right? So the change in magnetic field will be this, positive 312, and then milliteslas is, of course, times 10 to the minus third, right? Okay. And then the area will be pi r squared. Be careful of the diameter. Be careful of centimeters, right? Okay, so half of that, right? 0.035 over 2 is going to go in for your radius, right? So that'll be your area. Change in magnetic field is that. Time is 0.520 seconds. right? So that's your rate change of flux, right? Then it says, what's the induced EMF? Well, the rate change of flux times the number of windings will give you that. Okay, so don't forget the N, right? And then as far as the negative sign, that's all wrapped up in whether it's a north pole that way or a south pole that way. And it doesn't really make sense to us. But in this case, by the way, we would create flux. If it's increasing to the right, we'd create flux to the left. And the way to do that is the current would go up the front of the coil. And it would register a positive EMF on the data logger. That's not asked here, but there you go. All right.